All right.
Wonderful. Thank you so much.
All right. Thank you, Morgan, for the introduction, and thank you, everyone, for being here today. My name is Malena Rice, and I'm a fourth-year PhD candidate in the Yale Astronomy Department, working primarily on the dynamics of planetary systems. So that, for me, that includes both the solar system as well as extrasolar systems. And today I'll be sharing with you a really fun project, I think, putting together an all-sky survey of the distant solar system by shifting and stacking data from the Transiting Exoplanet Survey Satellite, which is also known as TESS. The focus of this survey is specifically on solar system objects that are at magnitudes below the TESS single frame detection limit. So many objects need to be stacked in order to actually pull out the signals of these objects. So some of this presentation will be based on a proof of concept that I published in 2020, but I'll also dedicate a fair bit of time to updates since that paper and a couple of new directions towards the end of the talk. So this is ongoing work, and I'm really excited for the discussion and to hear everyone's input and other ideas that you might have. Of course, I'd like to start off by acknowledging that this project was actually inspired by two papers led by scientists here at the CFA. So it's really exciting to be here and to share my work at the same place where some of that foundational groundwork was laid. All right, so to motivate this project, I wanted to also just begin with an overview of the parameter space that is spanned by known objects in the Trans-Neptunian solar system. So shown here is a map of the known objects in semi-major axis versus eccentricity space, including delineations into a few different populations. That includes the scattered disk, the classical belt, the centaurs, and the detached Kuiper belt objects. Something you might notice is that as we move towards increasingly larger semi-major axis, there are fewer objects that are known, specifically at the lower eccentricities, and that's just an observational bias that just is showing that with current surveys, we can only see the most eccentric objects in these populations as they reach perihelion, bringing them relatively close to the sun, so within about 100 AU or so. Of these distant objects, there are only about a handful that orbit entirely exterior to Neptune's orbit. So this is just a few objects that can't be directly scattered or dynamically interact with the solar system planets. And these are the detached Kuiper belt objects. They've been the subject of a lot of debate over the past few years. And so because of this, they're also the primary population that we're targeting within this survey. In 2014, Shepard and Trujillo found that the arguments of perihelion of the long-term stable detached Kuiper belt objects appeared to be clustered in one particular direction on the sky. And this is not expected because the orbits of these objects should precess over time at different rates that would cause them to spread out across the sky over a timescale of about 1 billion years. So nothing in the solar system is actually in a nice, pretty two-body system. We have deviations from a Keplerian potential, particularly due to the outer giant planets in the solar system, which we can approximate by summing over the perturbations induced by those giant planets in the secular approximation shown here. And that deviation means that the orbits of your objects don't perfectly close and they should spread out. But they appear to be clustered on one side of the sky. And then similarly, Batigan and Brown in 2016 showed that the longitude of ascending node, which tells us the relative plane in which each of the orbits lies, also was found to be unexpectedly clustered. And we wouldn't expect to see that for the same reasons. So if this observed clustering is actually real and it's not an observational bias, it might suggest the influence of another body that can provide a restoring torque that prevents these orbits from spreading out. And that proposed body is known as Planet 9. I'll note that it's sort of contested whether or not this is real, and that's actually a big part of this survey where we're trying to figure out, we're not just looking for Planet 9, we're also looking for these Trans-Neptunian objects and seeing, are we able to put better constraints with one survey on whether or not this is an actual effect, or if it's just an observational bias from trying to combine multiple surveys that have different systematics. So if Planet 9 does exist, then the appeal of it is that it would be capable of restoring this, it would be capable of providing this restoring torque that would be able to prevent the precession of these extreme Trans-Neptunian objects. And it would also be able to provide a mechanism to create detached Kuiper belt objects, to create high inclination orbits of objects such as centaurs that are a little bit more difficult to explain with some of our current dynamical models. The most up-to-date parameter ranges for Planet 9 are shown on the bottom right here. And so it would be a super Earth-sized planet. It would be really exciting if it did exist, because that would allow for in situ observations potentially of a super Earth. So it's sort of worth pursuing to see if it does exist, because it would teach us a lot if it was out there and if we found it. So this is just a slightly more visual depiction of what Planet 9's orbit might look like, so what those orbital elements actually mean. A few different groups have been searching for this planet in a variety of ways since it was proposed. So the first method you can use is dynamical analysis to narrow down where the planet could be based on how it would interact with various solar system minor planet populations. So this is just showing the level curves of a Hamiltonian that I plotted up for a couple of different locations of TNOs for a fiducial Planet 9. That's just the middle values that you would expect from the initial proposals of what Planet 9 would look like. And you can see that for certain locations of these TNOs, you would get libration in the orbital angles of the objects. And so that means you would get a clustering of objects with this omega angle in one particular direction of the sky. That's the same apsidal alignment that we saw in the earlier slide. Whereas the objects that are a little bit closer in the solar system, so at 150 or 250 AU, would not show that same clustering. So this is sort of the type of argument you can use. You can say, we're going to put Planet 9 in a simulation, and we're just going to see what type of planet would produce the same dynamics that we observe in the outer solar system, and try to narrow down the region of parameter space that it would fit in. Another way is you can use gravitational probes. So we can narrow down where a planet can be based on the locations of objects with a known solar system ephemeris. The United States tracks the locations of its spacecraft using radio telescopes in the Deep Space Network, which can pinpoint the locations of these spacecraft in the 1D line of sight direction to within just a few meters. So for example, the Cassini radio ranging data was used by Fieng et al. 2016 and Holman and Payne 2016 to suggest likely regions of parameter space for this planet. And an issue here is that it can be pretty easy to mistake signals from undiscovered Kuiper belt mass with a signal from Planet 9. There is a lot less material in the Kuiper belt, but it's also a lot closer to us. And so the magnitude of the signal that you would get from the Kuiper belt, which we don't actually know where all the material is because it's in a lot of very small bodies, would produce a larger signal than Planet 9 would. So this is a problem that can be mitigated that I did explore in past work. So I showed in a 2019 paper that it would be possible to use a network of small telescopes to pinpoint the locations of many solar system asteroids using occultations, which would provide the necessary precision to find or substantially narrow down the region of parameter space for Planet 9. The idea here is that objects passing through the solar system will sometimes occult background stars. And if we can measure those occultations, then we can figure out exactly where those asteroids are in space to the same precision as where the background stars are, which is now much better because of the Gaia mission. So with many of these precise positional measurements taken across many objects, this is sort of like having a lot of different Cassini spacecrafts and being able to say more definitively with a lot of different probes if you see a statistical perturbation in one particular direction that might correspond to Planet 9. So this is a way that you'd be able to use actually just what exists in the solar system already in order to pinpoint where Planet 9 could be. And this is just showing 2-scale Jovian Trojan asteroid Patroclus Menetius, probably pronounced that wrong, passing over the United States. And so you can see the size of its shadow as it passes over, and all the different telescopes that it would cover up. And so there are a lot of asteroids that you'd be able to follow up. The problem is that you would need to follow up each individual asteroid several times. And so it'd be quite expensive to just fly around the world to try to do this. And the idea there was that if you had a robotic network that was just continually observing, it would be possible to actually accomplish this. These would be relatively small telescopes, 16-inch or so, but that's still not terribly inexpensive to implement. And so that brings us to direct reflected light searches. This is also not always easy to implement. It's kind of expensive as well. But fortunately, there was already a spacecraft that was completing an all-sky optical survey. That is the Transiting Exoplanet Survey Satellite, or TESS, that I mentioned at the beginning of the talk. So this is just a video that's showing what exactly it is that TESS observes. It has 4 different CCDs, and you'll see it sweep around the sky, observing different regions of the sky, and eventually it gets around pretty much the entire sky. TESS is an Earth orbiting satellite. It was designed to search for transiting exoplanets around bright nearby stars. And while this isn't actually the mission's primary case, it's actually really ideally suited to search for these distant objects that are dim and slow moving in the outer solar system. So TESS observes each region of the sky for about a month at a time, collecting a huge number of photons from each individual object in the frame, especially these really dim objects that are moving very slowly and stay in the frame for the entire 27 days. Here you can see there's a gap in between the northern and southern surveys, and that's actually where the solar system lies. So this is the ecliptic plane, and TESS is observing all of the higher inclination space, which is where we would expect Planet 9 might potentially exist. It should be on a relatively high inclination orbit. TESS's cameras are actually very conveniently aligned parallel to this ecliptic plane, which means that distant solar system objects that move within the plane or somewhat close to the plane, they cover only a small orbital arc over the span of the TESS mission, the objects that we're interested in that are very far away, and they should just be moving effectively from left to right. And the reason for this is we're just seeing the Earth's parallax motion as the Earth is moving past these objects that are very far away. And so the fact that TESS has its cameras aligned parallel to the ecliptic means that a ship stacking search really only needs to look at a certain region of parameter space. It just needs to look at paths that are moving mostly from left to right, because we're just looking at the Earth moving past these objects. So the 2 initial feasibility studies on this topic demonstrated that known trans-Neptunian objects can be recovered by shift stacking, and they stated that it should be possible to actually discover up to hundreds of new objects by searching along all possible orbital paths. This is a really cool opportunity, actually, to use a space-based all-sky survey to search for high-inclination solar system objects that are rare but are also really dynamically interesting and can tell us a lot about the history of the solar system. So to realize this idea, we developed a shift stacking pipeline that's designed to process TESS full frame images and search for the signals of dim outer solar system objects below the TESS single frame detection limit. And this pipeline involves first masking out the brightest pixels. So we're just reducing noise from stars in the frames. Then we subtract away the baseline flux of every pixel. We need to do that because we're looking for systematic increases of above the baseline flux that occur along a path. And then lastly, we shift and stack the frames along all plausible paths in order to search for these new objects. So a little bit more concretely, we can consider the example of Sedna, which is a V about 20.6 extreme trans-Neptunian object. Sedna is in the pixel with a black dot in the TESS frame to the left, and it's in the pixel with a red dot in the TESS frame to the right. So you can't really see any obvious changes in flux from just this photometry because it's so dim. And so what we do is we take the full time series, we just ignore sort of these data downlinks that occur at the beginning, middle, and end of each sector. And then we fit some model to each side of each pixel's light curve, subtract it away until we get effectively noise. And then we end up with just this nice noise image. And that's great because what we're looking for is actually just tiny deviations above that noise. So you're not going to be able to see any of this by eye. Once we've done that, we can then look for objects that are actually moving across the frame that are extremely dim. So if you're looking for an object that moves across the frame like this, then you could equivalently follow the frame of the object instead and slide the image past. And so that's sort of the idea of shift stacking, where you're sliding the image's path to follow the path or to follow the frame of reference of the object that you're looking for. This is an example video that's just showing how we shift stack to recover Sedna's flux. And so what you see here is in the left frame, we've masked out all of the foreground stars or all the background stars. And so what you end up seeing is foreground asteroids that are just passing through the frame. So once we've gotten rid of all the extremely bright things in the frame, then you end up with the slightly less bright things that are just asteroids passing through. And then on the right side, we are showing the recovery of Sedna over time. And so here we are sequentially summing the images as they show up on the left. And we start off with this big gap on the left side of the right frame that ends up being filled in over time as we shift and stack to get this nice little dot that is Sedna. And so this is sort of how we are able to extract the signals of individual objects that we know of already using shift stacking. And that's summarized by the first 3 slides that are shown here. And this is sort of showing how we can extract the already known objects, but we want to take this a step further and also find undiscovered objects. And so what we do there is we create something that we call a best ever frame, which is an aggregate frame that retains the highest flux from all of the tested shift stacks at a given pixel. So in order to create this frame, we check all the different paths of interest and find the highest summed flux that is attained along all paths. And this ends up leading to a final data product that looks kind of similar to an image, but it's a little bit different. It's actually an information dense aggregate that condenses all the information from all your shift stacks into one image. And then you can pick out what looks like real signals, conduct the standard shift stack. So just do what we did on the previous frame and see if you get a signal that looks like a realistic object. So this is kind of a way to pull out the most promising signals and look at all of your shift stacks at the same time. So we demonstrated our object to recover objects, or 3 different objects that are below the TESS single frame detection limit here. So these are 3 different Trans-Neptunian objects, Sedna, BP519, and 2007 TG422. And these are the 3 rows that are shown in descending order of apparent magnitude. And in the first column, we just shift and stack the frames along the object's known orbital paths. So this is like the video that I showed earlier. But in the second and the third columns here, the recoveries actually incorporate no prior knowledge of the object's orbits. So here we're shifting and stacking along all possible orbital paths, assuming linear paths that are dominated by the Earth's motion between 35 and 800 AU. And we end up having nice signals of Sedna and BP519. TG422 was not recovered with this blind search, and that's probably because of a combination of 2 factors. The first is that we think this is about what our detection limit is. It might be slightly below our detection limit with this search in terms of magnitude. So this is the dimmest of the 3 objects. And the other reason is that TG422 is the most nearby of these 3 objects. So it's at a distance of about 37 AU away from the Earth. And what that ends up meaning is it has a more nonlinear path because you get a larger contribution in the TESS frame from the object's actual motion instead of just the Earth's parallax. And so because you have the object that's actually moving on a larger part of its orbital arc, you're not going to be able to capture the entire arc in a linear shift stacking search. And so because of that, it's sort of challenging in 2 different ways, because it's relatively nearby as well as because of its magnitude. We used injection recovery tests to understand the completeness of our detection limits using 2 different baseline subtraction methods that we applied in our blind search. So we selected a random cutout region from each of the TESS CCDs, specifically looking at a region along the galactic plane, with the motivation that we want to understand what our detection limits are in the most challenging region of the sky before we then go for a full sky survey that will then perform better in the cleaner parts of the sky. But we want to know how well we can perform in the really tough parts of the sky as well. Here we injected a grid of 24 signals at each magnitude and X shift into each of these frames. And X shift is a proxy for distance because this just quantifies the rate at which the signal moves across the sky. So this is the number of pixels that it spans over a TESS sector. Then we ran our pipeline using 2 different baseline subtraction methods. So we used a polynomial fit where we just fit simple polynomials to the baseline of that pixel. We also used a principal component analysis baseline subtraction where we were looking at surrounding pixels in order to determine the baseline of that individual one. And we find that, first of all, our survey is mostly complete for objects to about 21st magnitude and around 150 AU. So that's about a 25 to 30 pixel shift. And so you can see we have mostly blue to purple diamonds that are in that region. And that's in the galactic plane specifically. The performance would be a little bit better outside of the galactic plane. And our PCA baseline subtraction method also performs generally better than our polynomial method, and that's because we don't get as much self-subtraction. So we're looking at other pixels in order to determine the baseline of a given pixel. And that's going to be really important for these really slow-moving objects like Planet 9 because they stay in one pixel for a really long time. And so it's very easy to just subtract away the signal of the object if you're just fitting to the baseline of that pixel itself, because it'll stay in one pixel for most of the time that it's being observed. We also quantified our detection limits specifically for more Planet 9-like objects, and we found that we're sensitive out to about 20th magnitude or so in the galactic plane using the PCA subtraction. But I would like to emphasize that this first paper was really intended as a proof of concept. So since then, we've done further work to refine our methods before extending to the all-sky survey. And so here you can see our published best ever frame recovery of Sedna. This is the initial recovery that we showed a couple of slides back. And if we mask out the foreground asteroids, then we can refine that return signal and just get rid of a lot of the streaks that showed up. And then with a couple more adjustments to the pipeline, so more careful stellar masking, maximizing the number of data frames that we preserve within our recovery, we're able to extract this signal. And this is, again, a best ever frame. So this is searching over every possible path in that region of the TESS frame. And you really just get a signal from Sedna. You're not seeing really any substantial systematics in this frame. This is what we're trying to get all of our signals to look like before we do an all-sky search, because we want to make sure that our limits are not in our methods and that it's really a limit of the data set. So we want to hit the magnitude limit that is possible to hit with TESS by being as careful as we can with all of our pre-processing methods. So the primary goal of this work is to extend this project to an all-sky survey that is incorporating neural networks. So it is quite a lot of data to go through all the TESS primary mission, but then TESS is actually also continuing to observe. So you can just continually run all of the sectors through this type of search. This would streamline the candidate identification process, but it would also help us to better understand what our false positive rate is going to be. So we inject signals into our data set and better understand what types of or what region of parameter space we're actually sensitive to. Throughout this talk, I've also been really focused on the very distant solar system objects, but it's also possible to extend to other populations. So on this map alone, there are a lot of different populations that could be explored with the same methods. TESS surveys the entire high inclination sky and will also be looking within the solar system. So it's going to be filling in a lot of the space that it didn't observe before over the coming years. And so there's a lot that is there to be mined and that hasn't really been explored so much for the purposes of studying the solar system just yet. One example population of potential interest is the interstellar objects, and that comes to mind because TESS is observing the high inclination sky. Interstellar objects generally come from very high inclinations, and you can see the orbits of the two that have been observed so far within this simulation here. In particular, something really interesting about this is that those two objects both came from the same direction in the sky. They came from the solar apex, which is the direction that the sun travels in the galaxy relative to the local standard of rest. And that's not actually too far off from the TESS continuous viewing zone, which is where TESS takes 350 days of continuous observations. So this could actually be a really good place to search to understand occurrence, or to place constraints on interstellar object occurrence rates. Previous studies that have extrapolated from the observations of the first 1 to 2 interstellar objects, so that's a big asterisk because we actually haven't seen that many, but extrapolating from that, it seems like there might be a lot of these objects out there. And so it might be possible for TESS to find individual objects, but even if not, it could be used to place limits on what should have been detectable. And it could be a really good survey to accomplish that. A shift stacking search for dim nearby objects like interstellar objects is going to require nonlinear shift stacking. So you can't just do a linear search the way that we have been in this initial survey. This is something that I have been actually working on. I developed a program that converts directly from orbital elements to the sky projected locations of objects as viewed by this TESS spacecraft. So these are just a couple of sample tracks in the top left here. And with that, we're now injecting signals on randomly sampled orbits into our data frames to better understand what kinds of signals are extracted by our neural network, and to delineate that parameter space and to better understand, should we be doing a nonlinear shift stack? Should we continue doing linear shift stacks just in particular regions of parameter space? And to figure out what we would expect to be able to accomplish with each of those approaches. I also want to note that the location of these objects as viewed by TESS is a little bit different from as viewed from the Earth, as shown in the bottom left here. So TESS is on a really highly eccentric orbit, and you need to start taking that into consideration for objects that are a little bit closer in. So our first search was just focusing on objects like 70 AU or farther from the Earth. You don't really have this problem, but once you start getting a little bit closer in, you really do need to take it into account. And then a last fun thing that I tried recently, actually based on a suggestion by Mike Alexanderson here at the CFA, is sequential summing to see if we can extrapolate any information about the shapes and rotational properties of the observed objects. So for Sedna, we don't really see any particularly obvious trends from this image in the top right. And I think that's actually expected because Sedna's just about large enough for gravitational forces to overcome rigid forces. And so Sedna should actually potentially be in hydrostatic equilibrium and would thus be round. So you wouldn't really see anything. But for more oblate objects, this could be really interesting to better understand the shapes, the shape distribution of these objects, including for known objects potentially, but also for these objects that we're searching for that have not yet been discovered. So I will leave you with my conclusions. Thank you again all for being here, and I'm excited to chat more about this.
Thank you so much, Malena. You can only hear me clapping, but we all really appreciate it. And I think there's really exciting stuff here as we think about, well, I don't know, on a personal level, I get really excited about work like this because it takes an instrument that we already have, a like capability that we already have, and we're kind of imagining what a totally different science application could be than the like original design. And we also don't have to wait a decade to start doing that science. So I think that's incredibly exciting. So as a logistical reminder, people who have questions, go ahead and text me in the private chat just a word or two about the topic of your question, and we can start a conversation there. So I'll go ahead and ask a first question. I'm curious about I guess about your outlook on, or if you could talk a tiny bit more about like expanding into the faster moving or the nonlinear motion that you were referencing. How do we do you envision that happening in a way that is essentially like totally blind or totally algorithmic, in the sense of like just like letting a neural network try to handle that? Or do you envision that happening in terms of like we encode, you know, the Keplerian motion and then like search in a more targeted way?
Yeah.
And if there are things that I'm missing, please go ahead and speak more broadly to that.
Yeah, so in a nonlinear shift stack, I've actually just been working on this, so I can pull up.
Amazing.
So I've been working on developing a library of just all of the, so this is the plot that you saw earlier, of all of the possible orbital paths that you can get. And there was an interesting work by Burkhard Raguseen and someone else a couple of years ago that was, they were finding the minimum number of these orbits that you can find that are overlapping little enough that you would expect to find the full range of orbits that you're interested in. And so the idea there is you randomly sample lots and lots of orbits over the entire parameter space. That's what I've been doing. I'm specifically right now focusing on objects from about 50 to 200 AU because that's the region of these extreme trans-Neptunian objects where there's a lot of debate. And so I've been working on just developing a library of lots and lots of orbits. And then once we have that, then we can actually narrow down and first of all, understand what types of orbits create, or what types of orbits create what kinds of paths. So you can just get a better sense of like, if we only look at the prograde orbits, then they look like this as opposed to this initial group. Or if we just look at the lower eccentricity orbits, then it narrows it down a little bit. And so what I'd like to do there is just, first of all, consider for all of the possible orbits, how many paths would you actually need to search? And then if you want to narrow down to fewer orbits, so if that might be sort of computationally intractable, if that's too many paths to actually search with this algorithm, then you can also narrow it down and just say, I'm only going to look for prograde objects that are at this range of eccentricities. That also helps to reduce noise in these best ever frames, because the more paths you search, the more noise you get. And so that's one of the main concerns that I have, is that I don't want to search too many paths such that the real signal gets drowned out. And yeah, so I guess the direction that I see that going is coming up with a library of the minimum number of paths that you can search to expect to actually recover all the objects in your expected parameter space, and then actually just shift and stack along those paths. And developing the library is actually the more computationally expensive part, because shift stacking is just like array operations, so it's pretty inexpensive.
Right, with these 2D arrays. Yeah, that's really interesting. And along those lines, does that relate to some of your comments on completeness? Because like you can understand whether, I'm making this up because I don't know, but like a very eccentric orbit would produce a path that's harder to detect or something like that. Like, does that relate to what types of orbits are easiest to find?
Yeah, so this tells us more about what types of orbits you can find with a linear shift stacking search.
Okay.
And so if the line is straight, then you can find it. And if it's not straight, then you probably can't find it, is effectively what that's saying. You can, again, extend to a nonlinear shift stacking search. It just extends the parameter space so that you might get more false positives. And so you have to be a lot more careful about actually interpreting your results once you do that. So that's something we've been actively thinking about how to do.
Interesting. Brad, do you want to go ahead and continue along these lines?
No, I think that's all been covered. Thanks.
Matt had a question also.
Yeah, and nice talk, Malena. It's really great to see this. I have a few questions, about some of them have already been answered, but so this is mostly about the sort of the details of the background subtraction. So it's really interesting to see, your approach of fitting the individual pixels. And I mean, I guess what you're also doing some PCA. So did you, examine options for kind of more conventional image subtraction? Because that was what I had kind of imagined anybody would do.
Yeah, do you mean just subtracting out the median from the TESS data set for all of it?
Or there are a bunch of different approaches where you're maybe not subtracting the median, but you have some transformation from each individual exposure to a template exposure. That, and I know that's really challenging for the case of TESS, because it's undersampled somewhat, and because there are distortions that have to do with the velocity of the spacecraft. But it was interesting to see that you took a more local approach that seems to be pretty effective, and I'm mostly interested in how you arrived at that.
Yeah, so in the more recent iteration that came up with this image, I actually did do a median subtraction before then implementing these other methods, but I found that when I used just the median subtraction, I ended up with a little bit too much noise where you couldn't really extract the signal as nicely. And I think it's just that different pixels are maybe affected more or less by locally what exists around them within the frame. So maybe if they are a little bit closer to a nearby star or something else. So the median subtraction I guess first of all, doesn't really get rid of the signals from surrounding stars. So that was kind of the motivation for just a direct polynomial fit, because then you know that if this pixel is a little bit closer to a star than another pixel, you're still subtracting the baseline in the same way.
Yeah.
The PCA method we found worked better. And what we're doing there is we consider a given pixel, we mask out the region within 5 pixels of that particular pixel, and we consider the n number of surrounding pixels outside of that aperture that we then use to determine the baseline subtraction. And so this is something that is implemented in the light curve package. It exists from the TESS team itself.
Okay.
And so that's something that we have used that we found more effective, I think, because it captures those local effects a little bit better, but it also doesn't consider flux associated with the object that you're interested in. I know that there are other kind of more detailed methods that do this as well, where they specifically look for just the regions that are farther from the stars and are a lot more careful about exactly what pixels they use in the baseline subtraction. And that's really the most important part in how well you can extract your signal, is really very, very directly based on how good your baseline subtraction is.
Yeah.
I know Dan Foreman-Mackey, who I'm working with on this, has a student who has been working on that, but he also mentioned that it's pretty computationally expensive. And so everything that I've been doing thus far runs within a day for a sector. So it doesn't take very long to run. And I'm a little bit hesitant to make it very computationally expensive, but
Yeah.
I'll see if it works much better, because it might be worth doing if it takes a few days versus a day. It just kind of slows down the timeline a little bit.
Yeah. And so a question related to that is your best ever frame. So I guess I don't really understand what, and maybe I should just look at the paper to see, how are you kind of compressing all of the results into one frame? And you kind of alluded to the noise from different solutions interfering. Of course, I know how shift and stack works, but
so I skipped over this because I I didn't have enough time to go over everything in detail. But what we're doing in the best ever frames is we're basically starting with a 2D array of zeros. We put our baseline subtracted image in it, and then we shift and stack along some path. And then we, at every pixel that has been covered here, check if the flux is higher than it has ever been before. So for the first shift stack, every positive value is retained. And then we keep that image and conduct another shift stack along another path and do the same thing. So then we compare with all of the other pixels that exist, or we compare with the previous values of those pixels and just retain the highest flux. And this is going to sort of add some noise, but it also creates a slightly more intuitive way, for me at least, to understand what the highest signal to noise results are in a given frame, because then you're able to maintain the highest flux that you get from every possible shift stack within just one image. And so you can compare all of the signals and false positives in a given image together all at the same time, as opposed to having lots and lots of different images that you have to check for individual potential signals.
Can I follow up on your comments on adding noise? So does it have the effect of, like, say you have a pixel which is particularly high background level, like, doesn't that smear it in every direction so that your background is like equivalent to whatever your worst deviation upward is? Or like,
yeah, so I think that would end up leading to effectively what you're seeing from these asteroids, where you would get sort of a streak in the frame. So we have streaks here. And so that also helps to, if you just had an individual shift stack, then you might just see this as a bright point. But with the best ever frame, then the signal sort of gets smeared across the frame, or you end up with what doesn't look like a real signal. And what I'm calling a real signal is one that has a high flux peak at the very center. So that corresponds to the best match in terms of the shift stacking path. So the linear path best overlaps with that particular path, and that then you get the highest flux, and then you get a tapering around it, and those are paths that are close to the right path but don't overlap entirely. So they overlap partially with the path of the object but not fully, and you end up with this nice sort of tapering off. And you can kind of distinguish that from like, this does not look like that, so you know that that's probably something else. Sometimes it's a little tricky with the stars, but usually they're kind of a little bit more uniformly a bright region as opposed to having a bright center that tapers off. Does that make sense?
Yeah. And Matt, I'm sorry to like derail things. Does that like taper? That's sort of, is that like, can I think of that as like a density of states or like a density of paths? Like, so that PSF is not like a point spread function in the traditional sense, but it's like a related to the relative density of possible paths or something like that. Can you explain that to me a little better than I just did?
Yeah, so I think I'm gonna see if I can try to explain this with maybe, so these are some actual paths that you might have across the frame. So say you're trying to recover this particular object. There'll be a linear path that best overlaps with this, but you could also have a linear path that sort of overlaps with the beginning part and then it tapers off and doesn't overlap with any of the rest of the signal, or that, I don't know, goes like this. And so you would still end up with some flux accumulation from that little part of the path that you overlapped with, but you wouldn't get the maximum overlap. And so what you're seeing is the maximum overlap occurs at the center, and then you have a tapering off that corresponds to decreasingly overlapping paths. And you can sort of see this also in these images. So an injection, a given best ever frame corresponds to this gradient in X shifts and Y shifts if it's a bright signal, where the center here that corresponds to this bright point is going to be the true signal, or the path that best overlaps with the real path of this injection. And then all of these other shifts are going to be sort of gradually approaching that, but are a little bit different. So maybe a path only overlaps with some portion, or it is like an object that moves just a little bit slower than your real object, and so it'll lag behind it a little bit. You'll catch a little bit of the outer region of the object's real PSF, but you're not going to be at the center of the object's flux. So you end up with a gradient like this, where the true signal is at the center, and then you have these X shifts and Y shifts that are close, but not exactly the right path. It's going to look a little bit less nice than this for nonlinear paths, but this was for a linear injection.
That's super interesting. That's super interesting.
Yeah, so it also provides a little bit more information for the neural networks to work off of, to have the best ever frames instead of the individual injected, or yeah, I guess instead of just the shift stacking image by itself. So we're trying to see if that helps us to reduce the false positives, and if the neural network can use this information, which if it's as clear as this, it certainly should be able to. It's just a question of, for the more nonlinear paths, if that might end up confusing the network in some way.
Interesting. Matt, back to you. I'm sorry to have put it in.
No, that's fine. I guess I have a number of comments that are probably just better offline. I mean, but I would point out that I think in terms of doing a complete search of the nonlinear paths, so that was something that Matt Payne and I kind of laid out in our proof of concept, and that's something that it comes from a paper that was led by Gary Bernstein, where we used HST to look for very faint TNOs. I know in the case of HST, since it's going around the Earth every 90 minutes, and the parallax of the HST at 40 AU is completely resolved. So, we had to kind of lay out a way to do a complete search where, the parameters are really about, they're really the standard sort of parallax parameters, like what's the, the distance, one over the distance to the object, and that kind of thing. And I could be wrong, but I think that that if you grid in that space, you end up naturally getting a complete search.
Yeah, that
And I mean, I'm happy to talk with you about that offline, because I know people have explored different ways, but I think that basis is, it's linear, orthogonal, and basically it's linear in the parameters, and takes separates out the motion of the Earth, and then the object itself is just the elements don't really matter, because all of these objects are more or less going on a straight line in inertial space. I mean, there's a little bit of curvature, but the main curvature you're seeing, if you pointed out, that's the Earth's curvature.
Right.
And anyway, I think that that's something that I'm happy to help you with, like point you in different directions. I think you would at least be able to. I mean, that was part of our calculation in the paper that Matt and I did. Like, how many computations would you have to do to be complete? And we use that basis just because it's tractable.
Yeah. Okay. Yeah. So the nonlinear part we've just started implementing more recently, because we were really focused on distant solar system.
Yeah, that makes sense. And you don't have to do, as you pointed out, for the distant stuff, you don't have to do. I mean, like, just linear on the sky is really what you're going to see first off.
That's really helpful, because we do want to extend inwards to at least 50 AU, because the ET go into there, and so that would be really helpful.
Sure. I mean, you'll find out that all the computation is on the stuff closest to the Earth. All the hard work is on the inner edge. So you're doing the right thing to proceed from outward inward.
Yeah.
Can I ask a sort of broad question that's related to that? So at, say, this isn't a well-defined question, but like at 50 AU or 100 AU or 200 AU, would doing an experiment like this in like a patch, like the test field, give us a sense of like, I don't have a sense of like how complete our census is of the objects as a function of distance. And maybe you do. And also, like,
maybe I should bring this up.
Can you do kind of like almost like a counting exercise in like how many objects you discover in a test pointing versus how many you knew about, or like to find out how much is there that is unexpected as a function of maybe magnitude or something like that, because obviously there's more little stuff than big stuff, but
yeah, sort of. I think it just depends on what population you're looking at. So for the very distant objects, these red dots are pretty much the only ones that are known. And so there aren't very many, and it's difficult to do a survey where you're trying to delineate how many there are as a function of magnitude, just because there are so few of them. But with that said, we really are, so I think that this gap here is the galactic plane, and the point of this survey is really to try to figure out whether this gap is actually there, or if it's just that nobody has really looked there. And so we're hoping that, especially with the shift stacking survey, you might be able to better figure out whether objects in the galactic plane or signals in the galactic plane are stars versus real objects, because if you see something that's moving in the galactic plane, then that's a little more compelling than a bright dot in the galactic plane. And so
totally,
that's kind of what we're trying to do, where we want to see if we can find anything here, or if we don't find anything there, that would also be really interesting. That would be maybe reinforcing that the alignment actually exists. But then we would have to be really careful about what do we actually expect to have seen there. And so that's why we're being so meticulous about these injections and making sure that they're as realistic as they possibly can be. And
that's really interesting.
Yeah, so the first project that the first paper that we published was actually just looking at sectors 18 and 19, which are along the galactic plane. But we do ultimately want to extend this, but our focus really still is on trying to figure out if there is something that's lost just within the galactic plane. We do have actually a list of 17 candidates that we found in that initial survey, but our methods have been refined a lot since then. We don't expect all 17 of those to be real, because these objects are just so rare that, if a couple of them were real, then that would be great, but it would be very strange to have such an overdensity in that particular region of the sky. And so we don't expect them to all be real. So we're hoping with these improved methods, we can, first of all, narrow down which of those candidates are really worthwhile to follow up. And then also extend to other regions of the sky, because the TESS data set, so this is sectors 18 and 19 shown here. The TESS data set also has sectors through this part of the galactic plane, through this part, through this part. So there's actually a lot there that can be explored. And we just looked at a small portion so far. But yeah.
And I mean, to step back even further, and this reflects my ignorance, is the rarity of those objects like that they're truly rare, or are there more that we don't know about? Or is that like, I don't have a sense of, I had always thought that there were more of those objects and we just are incomplete, but I could be completely wrong. So that, I think I was just wondering that also, like, do we have an expectation of the number that is truly there?
So if there is no actual apsidal alignment, and if this is an observational bias, then there should be more objects that are there that we just haven't seen, that would be at about the same magnitude, similar-ish orbits that are very highly eccentric, and objects that are sort of near perihelion. If that apsidal alignment is actually real, then maybe there isn't anything there. And so I guess that's the big question, is that we actually don't have a definitive answer to that yet.
Okay,
we're trying.
Understood. Yeah, thanks for bearing with me.
Yeah, no problem.
Well, on that note, I think we have a couple minutes left. Like, we've talked just now some about like where you see that going in the next steps. But if you want to offer us any other sort of final word.
Yeah, I think it'll be really exciting to try to understand this region of parameter space. I have not thought as much about going further in the solar system, but I think that's going to be also a really fruitful place to look once, especially once TESS actually observes the inner, or observes within the plane of the ecliptic. And so that's something that is sort of ongoing in the back of my mind, but because TESS hasn't observed it yet, hasn't been quite a priority. And yeah, I'd be interested if anyone has thoughts on, like, if there are particular categories of objects that would be really interesting to actually see if we can find like signatures of oblateness or something else within them. But otherwise, I think there are just a lot of interesting directions that this could go, both with TESS and also extending this type of search to other data sets. So this is something you can do with any data set that returns to the same region of the sky a few times every couple of days, maybe, or with some cadence that will allow you to actually link the same object to itself. And so, yeah, it's further extensions to other surveys are also something.
And that becomes pretty straightforward, especially when the objects themselves are so distant, right? Like these things, as you said, are moving really slowly across the sky. So like a 3-day cadence or something,
yeah,
is totally okay in the outer solar system. Is that right?
Yeah, that's
interesting.
Right. And
so like doing this from the ground is plausible as well, like, you know, with like an LSST type.
Yeah, this is definitely something you could do with LSST. LSST will be releasing its full frame images. I was talking to a couple of members of the team, and it's not yet known exactly how or in what format, but it will happen at some point during the mission. And so this is something that that team has been sort of thinking about implementing a shift stacking search as well. It will be a lot more computationally expensive with LSST. Yeah. So here we're working on the scale of terabytes for TESS, and for LSST it will be petabytes, I think, maybe more. So it does get very computationally expensive up to a point, but it's doable. You just need to have a very large computer or multiple.
Amazing. Well, I think maybe on that note, we should stop there. I think there's all sorts of interesting questions about how we do that on the computational level, but we can stop there. Thank you, Malena, for a really wonderful talk. Thank you for educating us, and it was really a delight to have this conversation. So thank you all for joining.
Thank you.